and welcome back to my channel A in Economist. So firstly, thank you so much guys for showing your love and support to my channel. And I'm very happy to share that within 4 months, we are now a family of 400 plus members. So it's, beyond my imagination, and I'm so grateful to all of you who have subscribed to this channel and showed your love and support towards me. So now let us get back to the topic. Today, we will be starting with a new chapter in time series. Specifically, we will go into what is parameter estimation. So we have already covered several, useful models in time series. For example, white noise, the moving average processes, the autoregressive processes, ARMA processes. Also, I have covered what is ARIMA and what is SARIMA. So all these models are covered as of now. And if you haven't watched that videos, I will give the link in the description. So please check that out. And after you complete this covariant stationary processes, get back to what is parameter estimation. So in each of this model, I have described what is the specification of this model. And there, I hope you have seen there are several parameters that are unknown to us. So in this chapter, we'll see how we can estimate those parameters and we can fit the time series model. And for that, we will specifically use three different approaches. As you can see on your screen, the first approach is the maximum likelihood estimation, which is also known as MLE. Then you have something called the Yule-Walker estimation, or what you also call as the method of movements. And the third thing, which I'm sure everyone is familiar with, is the least square estimation, or LS. Right now, in my playlist, I'll not cover this least square estimation because I have taught you that in econometrics playlist that I'll be uploading soon. So there I have covered in details what is least square estimation. So in time series playlist, I'll be only showing you what is a maximum likelihood estimation method and what is Yule-Walker estimation method, right? So let's start with this. In this video, I'll be covering what is maximum likelihood estimation. And from the next video onwards, I'll go into Yule-Walker estimation. So let's start with what is maximum likelihood estimation. So for that, let us start with a data set. Suppose your data set looks something like this: y1, y2, y3, up to yn. So this is a data set of size n, right? This is a data set of size n, which you have. Now, suppose, for example, this data set is drawn from a AR1 process, right? So you have a data set, and for simplicity, let us assume that this data set is drawn from an AR1 process. Now, how will this AR1 process look like? Yt is alpha plus phi, yt minus 1 plus epsilon t, where this epsilon t follows IID, normal, 0, sigma square, right? So this is the general form of an AR1 process. This I have, taught you in details. Again, if you haven't watched those videos, I'll be, giving the link in the description. So please check that out. So you have this data set, which is y1, y2 up to yn of size n. And for simplicity, we are assuming that this data set is coming from an AR1 distribution or AR1 process. And where AR1 process looks something like this: yt is alpha plus phi yt minus 1 plus epsilon t, where epsilon t has its own distribution. It is IID, normal, 0, sigma square. Now, the important question here is that what are the unknown parameters here? Can you identify the unknown parameters here? So alpha here is a parameter, phi is another parameter. Now, is it all that we have? If you look carefully, this process, there is another parameter which is sigma square, right? There is another parameter which is sigma square here. So altogether, there are three parameters, three unknown parameters in this AR1 process, where these two, alpha and phi, these two parameters, which we can, specifically see from the model here and here, is called explicit parameters. which you can explicitly see from the model itself, is known as explicit parameters, and sigma square is known as the implicit parameter. Sigma square is implicit because it, lies within the distribution of epsilon t. So it's not specifically mentioned, but when you mention the distribution of epsilon t, then only you get this sigma square parameter. So you have two kinds of parameters here. Alpha and phi, they are the explicit parameters, and sigma square is the implicit parameter. Now, how do you estimate this? Our main job here is to estimate these three parameters of the model using the maximum likelihood method. So, for that, what you have to do, the first step is to find out what is the likelihood function. Now, what do I mean by likelihood function? Here, I have given you a definition of likelihood function, which I have taken from Wikipedia. So I found it very helpful. So let's read this. A likelihood function is simply called the likelihood, measures how well a statistical model explains the observed data by calculating the probability of seeing that data under different parameter values of this model. It is constructed from the joint probability distribution of a random variable that presumably generated the observation. So I'll be writing what will be the likelihood function in case of this AR1 process. But as of now, just understand what is the likelihood function. Likelihood function measures how well a statistical model explains the observed data by calculating probability of seeing the data under different parameter values. And how you construct it? It is constructed from the joint probability distribution. This is the very important, point to remember, that likelihood function is nothing but the joint probability distribution of a random variable, presumably that has generated the observations. And I'll be explaining with the help of the, likelihood function that you see for AR1 process in a while. And when evaluated on the actual data points, it becomes a function of solely model parameters. This is also another important point. So this definition, again telling you, it's very, compact and it's very explicit, easy to understand. That is why I have given you. So the first step of calculating the maximum likelihood estimation is to calculate the likelihood function. And what will be the second step? Second step will be to maximize this likelihood function with respect to the parameters. Right? So now we will be going into these two steps one by one. So firstly, let us see how to write the likelihood function, which will be step one. Likelihood function, as I have told you, will be a function of parameters only, right? Model parameters. It becomes a function of the model parameters. So suppose that model parameters, here you have three parameters, alpha, phi, and sigma square. Suppose we call it a vector theta curl. So likelihood function, which is L, is a function of theta curl, which is a joint probability distribution of y1, y2, up to yn. That is what I have told you, that it is the joint probability distribution of a random variable presumably generated the observation. So basically, here the random variable is y, right? The random variable under concern is y, and this data set is generated from this random variable y. Data set is y1, y2, yn. This is generated from this random variable y, and that is the reason we are taking constructed from the joint probability distribution of this random variable from the observations. I hope this is absolutely clear now. If you match this expression, from the definition, then it will be more clear to you. So I know many students are confused why we, use this joint probability distribution. So I have told you the reason for that. It's the joint probability distribution where this theta curl is nothing but alpha, phi, sigma square. So this is basically a vector, column vector, basically, right? This is clear up till now. Okay. Now, how do you write this joint probability distribution? You can more explicitly write it in this way. If of y1, then you have y2 given y1. Then you have f of y3 given y2, y1. and it continues like this. Finally, you have f of yn given yn minus 1, yn minus 2 up to y1, right? So it is in the conditional form. So this joint distribution, since we know that epsilon t's are independent, IID. So if they are independent, then if you write the distribution of this and this joint probability distribution of suppose epsilon 1 and epsilon 2, so that can be written in the product form. But these yi's here are not independent of each other, right? Yi's are not independent of each other, so we cannot write it in the product form. So we cannot write it this joint distribution as f of y1 into f of y2, f of y3. You have to write it in the conditional form, since yi's are not independent. Only in the definition we know epsilon t's are independent. So here, this is another thing to note. And some people make mistakes here, so I have told you how to do this. So this is the conditional distribution basically. If y1, if y2 given y1, y3 given y2, y1, and it goes up to this. F of yn minus 1, yn minus 2 up to y1. Now, what is our job here? Our job here is to find out what will be this value, what will be this value, what will be this value, and what will be this value also. So every term. So we do not know what is the specific form of each of this term as of now. So our job is to find that out one by one. So let's see. We want to find out what will be f of y2 given y1. We want to find out what will be y3 given y2, y1. And we also need to find out what will be yn given yn minus 1 up to y1. So all these terms are unknown for us as of now with respect to this AR1 process. So we are basically finding out the parameters of AR1 using MLE, right? So let us see what will be all these expressions with respect to the AR1 process. For that, let us start with the model itself. Yt is what? Yt is alpha plus 5, yt minus 1 plus epsilon t, IID normal 0 sigma square. So what will be the value of y2? If you put t equals to 2, you have alpha plus y1 plus epsilon 2. This is the model. Now, once you know this, you can find out what will be expected value of y2 given y1. Now see here, if you want to find the distribution, this PDF, this is basically the PDF of y2 given y1, right? So what do you need to know to find out the PDF? You need to know two things again, expectation and the variance. So if you know the expectation and variance of, any random variable, you can find out the distribution. You know this main features, then you can write the PDF itself. So firstly, find out what will be this expectation. Y2 is as it is alpha plus 5y1 plus epsilon 2 given y1. Given y1 means y1 is fixed. Y1 is fixed. So alpha is fixed here. Pi y1 is fixed here. Plus expectation will be on epsilon 2 given y1. So this will be alpha plus pi y1 plus what will this be? What will this be? If you see, epsilon 2 also follows normal 0 sigma square. So what is the expectation? Expectation is 0 irrespective of the value of y. So this will be 0 and the expected value will be alpha plus 5 y1. Right? This is clear. Now find out the variance of y2 given y1. So variance of alpha plus 5 y1 plus epsilon 2 given y1. So this portion is constant. So variance will be variance of epsilon 2 given y1, which is simply, what will this be? Simply sigma square. So mean is 0 and the variance is sigma square for all t, irrespective of the value of t and y, this will be 2. So expectation is this and the variance is this. Right. Now, what do? We get this y2 given y1 follows normal distribution with mean alpha plus 5 y1 and variance is sigma square. Now, why it is normal distribution? Y2 is a function of epsilon t, y1 is a function of epsilon t. So the, y2 given y1, this is also a random variable. This will also follow a normal distribution. So basically, we know this, that if individually random variables are following normal distribution, their, linear combination or any, combination of them will also follow normal distribution. So you can think of this in that way. So epsilon t's are following normal distribution. Again, y2 is a function of epsilon t, and yt is in general a function of epsilon t. So any linear combination or any combination y2 given y1, the conditional, this random variable will also be following normal distribution with mean, this, and the variance that we have found. Okay, fine. So now that we have the distribution, we can simply write the PDF. What will that PDF be? Now understand this, when x follows, x is a random variable, when x follows normal 0 sigma square, what is the PDF of x? PDF is 1 by sigma root 2 pi e to the power minus half x minus mu upon sigma whole square. So this is how we write the PDF, right? X is a random variable if it follows normal 0 sigma square, this distribution. Oh, normal, sorry, mu sigma square, not 0. Normal mu sigma square, then fx is the PDF. Fx is nothing but the PDF of this random variable x is 1 upon sigma root 2 pi to the power minus of x minus mu upon sigma whole square. So in the similar way, here mu is this and sigma square is as it is. So what will be the PDF? 1 by sigma root 2 pi and then e to the power, let me erase this. Let me write here. So that will be 1 by sigma root 2 pi and then e to the power minus half. Then here you have y2. Y2, instead of x, you will write y2 minus alpha minus phi y1. That is x minus mu is this. So minus alpha minus this upon sigma whole square. I hope you understood this. This is the PDF of f of y2 given y1. And this is the first portion of the likelihood function also. This is what we found out, right? F of y2 given y1. In the similar way, we have to find out what will be f of y3 given this. Let's do that. What will be f of y3 given y2 y1? Let's see this. So for that, start with y3. What will be y3 from the model is y2 plus epsilon 3. Again, find out what will be this expected value of y3 given y2 y1. So expected value of alpha plus pi y2 plus epsilon 3 given y2 y1. Now here you don't have any y1. So you can get rid of y1 in the next step, y2 plus epsilon 2 given y2. So this is a constant since y2 is given. So what will be the expectation? This. Again, expectation of epsilon 2 given y2 will be 0. So this is what you have as the expectation. Now find out the variance y2 y1. So variance of alpha plus pi y2 plus epsilon 2 given y2 y1. So that will be simply variance of epsilon 2 given y2. That will be simply sigma square. So this is what you have as the expectation and this is what you have as the mean. And if you look at this, what we found earlier, you will see a resemblance. Variance is the same, sigma square, and here you have alpha plus pi y1 and here you have alpha plus pi y2, right? Okay, so what is y3 given y2 y1? This random variable will follow normal distribution with mean alpha y2 and sigma square. And again, we'll do the same thing. We will write the PDFs. F of y3 given y2 y1. That will be 1 upon sigma root 2 pi e to the power minus half y3 minus alpha minus pi y2 upon sigma whole square. So this is the PDF. Now, Let me do this. We got y2 given y1 follows normal alpha plus pi y2 sigma square. Then we got y3 given y2 y1 follows normal alpha plus pi y, sorry, this is y1 and this is y2 sigma square. So now I was telling you that find the resemblance. Here you have y1, here you have y2. Here you have y2, here we have y3. So this will continue to go on like this. So if you find y4 given y2, y3, y1, so this will follow normal alpha plus pi y3 sigma square. So here you have 4, here you have 3, here you have 3, here you have 2, here you have 2, here you have 1. Right? So you got the resemblance, right? So what will be in general yn given yn minus 1 up to y1? What will this follow? This will follow normal alpha plus pi 1 less yn minus 1 and sigma square is as it is. I hope this is pretty simple for you. So we got this, and using these two distributions, we can generalize the thing. Yn given yn minus 1 up to y1 is this. So this will be simply y of n given yn minus 1. So let me write it down. In short, what we can say is that yt given yt minus 1, yt minus 2 up to y1 will be in distribution following yt given yt minus 1, where this t is 2, 3, 4 up to n, right? So here this means same distribution. They are same in distribution. I hope you got this. And this is what we have shown, that y3 given y2 minus y1 is exactly the same as y3 given y2 because there is no term of y1 in the expression. Similarly, y2 given y1 and the rest of the terms. In general, yn given yn minus 1 and this will be exactly equals to yn given yn minus 1. Okay. And this is for an AR1 process. We are talking about AR1 process only. Right? Okay. Also, expectation of yt given yt minus 1 will be what? Alpha plus 5 yt minus 1. And what will be the variance? Variance of yt given yt minus 1 will be sigma square for all t from 2 to n. And the only things left to show is what will be the PDF. F of yt given yt minus 1 by sigma root 2 pi e to the power minus half yt minus alpha pi yn, t minus 1 upon sigma whole square for all t from 2 to n, right? So let's get back to the likelihood function now. Okay, so in this likelihood function, we have found out what is this expression. We have found out what is this expression. And we know all the remaining expressions since we found out the general term, this expression, yt given by t minus 1 basically. So we know all these portions. This is done, this is done, and this is done. So the only thing left is this, f of y1. What will be the marginal distribution of y1? And that is what is the final thing that we will do. Let's find that out. What will be the marginal distribution of y1? That is f of y1. So let's find that out. Now, if you have seen my video on AR1 process, I have told you what is the expectation of AR1 process. This is simply alpha by 1 minus 5. And what is the variance of the AR1 process? This is simply sigma square by 1 minus 5 square. This is the unconditional, basically, unconditional expectation and unconditional variance. If you haven't seen that video, I'll give the link in the description. Please check that out. So there I have explicitly derived how to find out the expected value of or the unconditional expectation of the variable and the variance, unconditional variance of the variable. So what we can write? We can write y1 in distribution follows normal distribution with mean is alpha upon 1 minus 5 and variance is this. Right? So what will be f of y1? 1 by sigma. Here sigma is this entire thing. Sigma root 2 pi e to the power minus half x minus alpha upon sigma whole square. Sigma is basically sigma squared upon 1 minus 5 square and the entire thing whole square, right? So we have got everything that we need to write down the likelihood function. See, we have this, we have this, we have this, we have this. So everything is explicit to write the likelihood function. So let us do that. Then the likelihood function, what we had earlier is y2 given y1. Now we can write this to be y3 given y2. The rest of the portion I'm not writing because I have told you they are same, yn minus 1. So this further you can write as y1 into product over t from 2 to n. And then you have yt given yt minus 1. So check this part. This I have written in this product form. F of yt given yt minus 1. So starts from 2 and ends with n. So 2, if you put 2, this will be y2 given y1. If you put 3, this will be y3 given y2 and so on and so forth. Now check that we have already calculated this. This is the marginal distribution of y1 and this is the general term. This is what we got here. This is f of yt. So everything is known to us where y1 and f of yt given yt minus 1 are as calculated earlier, right? So we know the entire likelihood function, right? If you write those, long terms here, you will get the likelihood function, and that is the explicit form of likelihood function for an AR1 process. So step 1 is done. So I have told you earlier that like in MLE, you have 2 steps. First step is, calculating the likelihood function that we have done. Now the second step is to maximize the likelihood function with respect to the parameters. So let's do that. And that will be the end of our session. Step 2. Step 2 is to maximize the likelihood function with respect to the parameters, which is alpha, phi, and sigma square. What does that mean? That basically means the first order conditions are like this. Take the partial derivative with respect to alpha and set it equals to 0. Take the partial derivative of this likelihood function with respect to phi, set it equals to 0, and take the derivative of this likelihood function with respect to sigma square and set it equals to 0. Right? This is what we do in order to maximize any function with respect to parameters. You take the partial derivative and set them equals to 0. And from here, what you will get? You will get 3 normal equations. You will get 3 normal equations. From this expression, what you will get is the first normal equation. Here, you get the second normal equation, and from here, you get the third normal equation as you do from the least square estimation method, right? So you will get three normal equations, and we know that there are three unknown parameters to be estimated. Three unknown parameters to be estimated. So you have three unknown parameters and three normal equations. If you solve them, you will get alpha cap MLE, you will get phi cap MLE, and you will get sigma cap square MLE. And that is how you find out the parameter, estimated value of the parameters for an ER1 process. I have not done this explicitly, this calculations, because, this will be abnormally long and I don't, see any reason to do this line by line. I hope you can do this. And this is for the general purpose of showing you the method of how to do this, right? So I'm not going into the calculations. You can, if you want, you can do these calculations, but this will be very messy looking calculations. You will not get any, good looking expression so that I can derive it. So I haven't gone into that, but if you want, you can do that on your own. So I have given you the entire process that you will get three normal equations and you have three unknown parameters. If you solve, you will get this estimated value of the parameters in terms of the known values of y1, y2, yn, right? These are the known values, and that is what you want, that the parameter estimated value of the parameters will be in terms of the known values of y1, y2, y. So this is all about the maximum likelihood parameter estimation. I have, given you the process for AR1, but we have something called ART process also that I will be discussing in the next class. So as of now, I hope you find this video helpful. Let me do a quick recap of what we have done. So we started with the maximum likelihood estimation method, where I have, taken a data set from AR1 process, that is size n. N data points are there from AR1 process, and we have three unknown parameters. So we wanted to find the estimated value of the parameters using maximum likelihood method. For that, what we have done, we have firstly written the likelihood function in this format, the joint distribution of these known values, and the function will be in terms of parameters only. L of theta coil. The theta coil is the column vector having all the parameters, right? And now I have, successively calculated all the components of the likelihood function for AR1 process, right? This is the general form of the likelihood function. And now for each components of the likelihood function, in case of AR1 process, I have, done all these things and I have shown you how to calculate them. And finally, what you have to do, you have to simply maximize the likelihood function in terms of the parameters. And that will give you your estimated. This is the, explicit parameters. This is implicit parameter. And that is how you calculate this. And thank you so much, guys, for watching this video till the end. And if you haven't subscribed to this channel, please do that. That gives me immense motivation to continue. And thank you so much once again for your love and support. And let's meet you in the next lecture. Thank you for your time.